Pipes are generally made of flat rectangular sheet welded in round shape and is open at both ends. Meanwhile, ducts are made of galvanized steel and are often insulated. Heat losses from a hot fluid flowing through an uninsulated pipe or duct can be very significant. Pipe or conduct flow may involve more than one form of work at the same time.
Traditionally, pipes are designed to carry liquid or gas at normal temperature and high pressure, but ducts are specially designed only for gases at elevated temperature and normal pressure. Pipes can be used to carry liquids such as water, sewage, gas. They can be seam pipe, sheet metal wrapped on a die and seamward or seamless. They can be used for transporting any entity like water or a structural element in construction of gaseous civil structure. But ducts are specially designed for particular purpose like rate of flow, temperature of medium flowing through it. There are many types of duct depending on type of material used for manufacturing like aluminum sheet metal, fiberglass, insulate duct. They may have variable cross-section which in case of pipe cannot happen. For example, consider the HVAC system in big malls and buildings which use duct to transfer cool air in every corner of building. These ducts have particular airflow rate and temperature specific. Ducts can be also be used in hotels, kitchen for sucking the smoke coming from cooking. Simple said, duct is a pipe, tube or canal which carries gas or liquid from one place to another, while pipe is wind instrument.
For the application of pipe and duct in real life, for the pipe, the example in real life is plumbing system. In plumbing system, pipes are used to transport fresh water to home and then distributed to sinks, bathtubs and others. Next, for ducts, the example in real life is the HVAC system. In HVAC system, ducts are used to deliver or remove cool air to different rooms and return back to HVAC system. So this is the other example of the applications.
From the question, it stated that steam enters a long horizontal pipe with a velocity of 2.5 meter per second. The inlet diameter of the pipe is 16 cm and the outlet diameter is 14 cm. The inlet temperature and pressure of the steam are 300 degrees Celsius and 2 megapascal respectively. Outlet temperature and pressure of the steam are 250 degrees Celsius and 1.8 megapascal respectively. The question asks to determine the rate of heat transfer in kilojoule per second.
For solving the question, few assumptions has been made. First of all, this is a stationary system where the change in kinetic energy and potential energy are negligible. Besides, it is a steady flow process where the amount of energy entering is equal to the amount of energy leaving. Lastly, there will be no work interaction. First of all, we need to identify the state of inlet stream. From the information given, we knew that P1 equals to 2 megapascal while T1 equals to 300 degrees Celsius. By referring table A5, the saturation temperature at 2000 kilopascal is 212.38 degrees Celsius. Since T1 is greater than T saturation, therefore it is superheated vapor, so we need to refer to table A6. At 2 megapascal and 300 degrees Celsius, the enthalpy of the vapor is 3024.2 kilojoule per kilogram, while the specific volume of the superheated vapor is 0.12551 meter cube per kilogram. Next, by knowing the specific volume, we can calculate the mass flow rate where it equals to density times velocity times area. Therefore, we will obtain 0.4005 kg per second. Now we need to identify the state of the outlet stream. From the information given, we knew that P2 equals to 1.8 megapascal while T2 equals to 250 degrees Celsius. By referring table A4, the saturation pressure at 250 degrees Celsius is 3976.2 kilopascal. Since P2 is smaller than P saturation, therefore it is superheated vapor, so we need to refer to table A6. At 1.8 megapascal and 250 degrees Celsius, the enthalpy of the vapor is 2911.7 kilojoule per kilogram. During steady flow process, the change in the total energy of the controlled volume is zero. Therefore, amount of energy entering will be equal to the amount of energy leaving. Since the kinetic energy and potential energy changes are negligible and there is no work interaction, we can define the rate of energy at the inlet to be mass flow rate times enthalpy, while the rate of energy at outlet is the sum of mass flow rate times enthalpy and the rate of heat transfer. By rearranging the equation, we can obtain the rate of heat loss to the surrounding, which is 45.1 kJ per second.